In this video, we will justify the statement that we made earlier in our discussion on length-preserving linear transformations, that if this identity holds for all vectors alpha, then necessarily Q transpose Q is the identity matrix. In other words, the matrix representing a length-preserving linear transformation Q is necessarily orthogonal. And I would like to note that this video makes frequent references to earlier videos in which we discussed matrix transposes, their products, and matrix products of this form. So you may want to review those videos before you watch this one. Now, getting back to the statement that we need to prove, we will actually go for a more general statement that has matrices A and B in place of Q transpose Q and the identity matrix, and that assumes that matrices A and B are symmetric. Now, why is it okay to limit our attention to symmetric matrices? Well, that's because both matrices Q transpose Q and the identity are symmetric. It's clear that the identity matrix is symmetric, but we have also shown that the product of a matrix and its transpose is symmetric no matter what the matrix is. So we're dealing with symmetric matrices here, so we'll limit our attention to symmetric matrices in the generalization. And the generalized statement sounds like this. If for two symmetric matrices, this product always equals this product no matter what alpha is, then necessarily A equals B. In other words, these products can be the same for all values of the vector alpha, only when the matrices are the same. And the assumption of symmetry is essential. It's not just nice to have or something that makes this argument easier to make. If the matrices weren't symmetric, then the statement won't be true in the first place. In other words, there could be two different matrices A and B, such that these products are the same for all alpha. I'll give you an example of that. Well, now let's get on with our proof. So here I have the schematics for these products. Here's the matrix A and here's the matrix B. We have to show that they're the same. Here's the vector alpha, its transpose, alpha itself, and its transpose. And the vector alpha is arbitrary, and we'll take full advantage of its arbitrariness. But remember that these four are essentially the same vector alpha. So whatever arbitrary numbers we put in here, we're constrained to put the same numbers here, 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 and here. All right, so we have to show that these two matrices are the same. So we'll show it in the opposite way. We'll show you that if they're different, then we can take advantage of the differences and come up with a very cleverly selected vector alpha, such that these products will end up being different. So we'll do it in two steps. First, we'll focus on the diagonal elements and then the off-diagonal elements. So suppose first that these matrices are different and the difference occurs in the diagonal elements. For example, this one is 3 right here and this one is 4 right here. That's a diagonal entry. All right. Well, I'm about to take advantage of this discrepancy and choose a vector alpha such that this product is different from this product, which shows that this cannot happen. The diagonal entries must be the same. Now, I'll just remind you of something that we learned before, that when we're dealing with products like this, let's assume it's 3 by 3. Then this product, which is just a number, a 1 by 1 matrix, is the sum of 9 terms, assuming this is a 3 by 3 matrix. And each one of the 9 terms has an element from this matrix. And let's say if we have an element right here, then it will involve, where am I? Let's say here, second row, first column. That it will multiply within its term, the term that corresponds to this entry, by the second entry from the vector on the left and the first entry from the vector on the right. And that's what the 9 terms that are all added together as a result of this matrix product. So now, with that in mind, I'm about to take advantage of this discrepancy. And I'll do it like this, by putting a 1 here and zeros everywhere else. And as I'm doing it, I would like to note that this argument works not just in 3 dimensions, but algebraically. Right? This came from geometry and length preservation, but what we have on the board now is pure algebra. So this holds in arbitrary dimensions, and the argument would be the same in all dimensions. But in any case, well, not in any case, that's an important note, so ponder it. Okay, but here I chose a vector that will take advantage of this discrepancy, because when we look at this product, because of these zeros, regardless of what else is in these matrices, right, the only surviving term will be 1 times 3 times 1. And here the only surviving term will be 1 times 4 times 1. So this product will be 3, and this product will be 4. And so we have shown that if these matrices disagree in their diagonal entries, then there do exist alpha such that this product is different from this product. So this no longer equals this for all alpha, and the presumption was not true. So this is proof by contradiction. So diagonal entries cannot be different. They must be the same. So if that's a 3, this must be a 3 also. So we have to focus on the off-diagonal elements. Now suppose that the off-diagonal elements are different. Well, because we're talking about symmetric matrices, this is not a free-for-all. There is some coordination. For example, if there is a 7 here, there must be a 7 here. And then now when we're talking about this matrix, if we're assuming that this matrix differs from this matrix in these off-diagonal entries, the number would be different, but the two of them still have to be the same. All right? And now I will come up with another vector that takes advantage of this discrepancy. Okay, but recall that it doesn't really matter what this number is, but because it's a diagonal entry, it must be the same for both matrices. Doesn't really matter what it is. So here is the alpha that will take advantage of this discrepancy to produce different values for these products. I'll just put 1 and 1. You could have seen it coming, but there it is. So now when we multiply this out, there will be 4 terms here, all added together into a single number. 4 terms here, all added together into a single number. Let's think about what those terms are. There will be 3 times 1 times 1, both for both cases. 13 plus 13 times 1 times 1, so plus 13. The same in both cases, except here we'll have 7 times 7 times 1 times 1, plus 7 times 1 times 1, so plus 14. And here we'll have 8 times 1 times 1, plus 8 times 1 times 1, 16. So this would be whatever part is common, so 16 plus 14. And this will be 16, which is the same, plus 16, which is different from the 14 we had over here. So if the discrepancy occurs in the off-diagonal entries, then it's a different vector that exposes that discrepancy and produces different values for these products. So that cannot happen either. So if this holds for all vectors alpha, then all of the diagonal entries match, all of the off-diagonal matrices match, and that means that the matrices themselves match. So we have proven our statement. In fact, we've proven something a little bit more general. Now I just want to show you that the requirement of symmetry was essential. And here's a very simple example. Instead of an 8, I'll put a 6. So let me describe the difference to you. We have 7 and 7 here. And here I added 1 to this 7 and subtracted 1 from this 7. So as long as you do this sort of thing, add something to this entry and subtract that same value from this entry, which obviously breaks the symmetry. So it's not really a counterexample to the statement that we were going to prove. We're still good. But I'm just showing that if these matrices weren't required to be symmetric, then we can have 2 different matrices, but these products are still the same. Well, these values don't equal these values. But because they're always in a sum, and you will see if you were to multiply these out, even if these weren't both 1, so let's say it's 1 and 21. No matter what you try for the vector alpha, when you multiply this out, right, things will factor out, and in parentheses you'll have 7 plus 7 here, and 8 plus 6 here. So for products like these, it's only the sum of these two entries that matters. And that sum can be broken up between the entries whatever way you want, and it doesn't affect a product like this. That's why if matrices are not symmetric, these products are the same if the diagonal entries match and the off-diagonal entries add up to the same value in this pairwise across from the diagonal sense. So that's why the requirement of symmetry was essential. And just one last note, I'll let you work out the details, but here we chose to work with entries that are next to each other. If these off-diagonal entries occurred far away from each other or in a higher dimensional sense somewhere in random places in the matrix, you would simply have to match up your vector alpha with those locations and put these numbers, which we'd right now put in entries 1 and 2, into the appropriate locations. I'll let you work out those details on your own. But we have accomplished the goal of proving that this identity holding for all vectors alpha necessarily implies that Q transpose Q equals the identity matrix, which is the definition of a matrix being orthogonal, which is exactly what we set out to prove.